Okay, uh, welcome back. So this is lecture 13. We're sort of at the halfway point. And I mean, today's lecture is going to be more like a build-up to what is going to happen in the next few lectures. And I guess, in this lecture and the next lecture, there is some patience that is required because I'll be telling you a bunch of tools and properties and so on. And it may be the case that it's not clear exactly why those are necessary. But just bear with it because we'll soon get to all that. So I'm trying to reveal these basic properties, etc., on a need basis, so that I don't just have one or two lectures on preliminaries and just tell you everything that I know about these things and then use all the things that we have. So which is why I'm sort of slowly giving you bits and pieces of information that is relevant for what I'm doing next. So it's maybe not the most efficient way of doing it, but in some sense, I'm hoping that the retention is better. Okay, so in this lecture and the remaining few lectures in part 2, the goal is going to be to do polynomial factorization. I mean, this in some sense is the punchline for part 2. Okay, and in order to do this, there's a whole bunch of tools that we will need to end up learning. Okay, and so in particular, we will need to know a reasonable amount about what finite fields are, even if it is the case that you are dealing with only integer polynomials and you want to factorize integer polynomials. Surprisingly, finite fields play a very crucial role there. Like, in fact, it will reduce the problem to something about finite fields and try and lift it somehow. So that's what will often happen. And so therefore, we will need finite fields and a whole bunch of basic properties about fields. So that's what I'm going to slowly try and tell you today, and we'll build towards a factorization algorithm in the next few lectures. So this is going to be like a sort of a marathon, which we will take slowly. Okay. So just a quick recap, and in fact, especially things that we may need, the rest of it, we can sort of put it in the back burner, which is that we saw a whole bunch of linear time algorithms. But from this point onwards, I'm not going to insist on the fact that algorithms need to be linear time. I am okay with polynomial time algorithms because I am going to look for some polynomial time algorithm for these factorization problems. So I'm not going to insist on something as strong as near linear algorithms or something. But nevertheless, in the course of looking at polynomial multiplication, we noticed this notion of quotients and remainders, which is what is this? The Euclidean property that you have whenever you're given a polynomial f and another polynomial g, which happens to be monic. Once you know that g is monic, there is a natural way to run your division algorithm. So you get a unique quotient and a remainder. Okay, and we use these sort of ideas to do multi-point evaluation, and you will soon see that you can also do Lagrange interpolation fairly quickly. Okay, so and the quotient and remainder was we also generalized this notion of taking general quotients of rings with respect to ideals. And quotient and remainder is in some sense like one very specific instance where the ideal is generated by one polynomial. So the remainder happens to become the representative of that quotient in some sense. Okay, so before I just proceed with, okay, let me stop this, whatever, the join sound. Sorry, just give me a second. So before we proceed with exactly what we are going to do, I want to sort of give you a roadmap of, roughly speaking, what's going to happen. Okay, so we're going to do polynomial factorization, but the natural question you may have is like, what sort of polynomial factorization? Are we dealing with, say, univariate polynomials? Are we dealing with bivariate polynomials, or maybe multivariate polynomials? And over what field? Are we dealing with integer polynomials? Are we dealing with polynomials whose coefficients come from some finite field or whatever, etc.? But we will try to do all of them. And we will soon see that once we see a little bit, it will naturally generalize to many other settings. But the point is, we will need to pick up a whole bunch of tools in order to complete this, this journey. Okay. The first thing we will need are something like basic field theory primitives, which is going to be the focus of today, like just getting comfortable with some fields. And then there is something called the Chinese remainder theorem, which I'm sure you have encountered in other courses. Okay, but Chinese remainder theorem can be stated in a slightly more general setup where there are ideals involved and so on. And we will see that version of Chinese remainder theorem because that's going to become crucial for our factorization algorithms. And something that you have already seen, like sort of one example of, are these Newton iteration or Hensel lifting. We didn't give, I just mentioned these, which was this idea of iteratively coming up with better and better, better and better solutions in some sense. You start off with a stupid solution and you perturb it to get a better solution and then get a better solution, etc. And this is something that we used when we did polynomial division, when we wanted to find the inverse of a polynomial mod x power 100 or something like that. So again, that is something that we will see in more generality, and in this more general setup is called either Hensel lifting or Newton iteration, depending on what sort of algorithm works. And then at some point we will start looking at lattices and computing shortish vectors in a lattice and so on. And so those are all the tools that we will need to do polynomial factorization. So as you can imagine, there's a lot to do here, but we're going to take it slowly and we're going to slowly build up and figure out what to do. And in fact, there's a rather funny way in which these three parts we will end up doing. The first thing we will do is we will try to do univariate factorization where the coefficients are coming from one of these finite fields. Okay. And then we will do bivariate factorization where the coefficients are coming from finite fields. Okay. And then we will notice that once we know how to handle two variables, it will sort of become clear how to handle many more variables. I mean, it will have all the necessary tools you need for multivariate factorization in general. But once again, we are dealing with finite fields. And surprisingly, once we know how to do bivariate factorization over a finite field, we will figure out how to do univariate factorization over, say, the rationals or integers and so on. So it's a little bizarre that somehow things will become clear when we eventually get there, is that factorizing polynomials with integer or rational coefficients has a lot more to do with factoring bivariate polynomials over finite fields, rather than factoring univariate polynomials over finite fields. I mean, once we set up the machinery for bivariates, I mean, doing this will sort of be almost like a plug and play with one extra click. Okay, so the order in which we are going to do things is going to be a little bizarre. I mean, it might seem a little counterintuitive at first, but I hope that by the end of this marathon, you will understand why it is the way it is. That there are good reasons why the ring Z, or the ring of polynomials over integers, looks a lot like the ring of bivariate polynomials over finite fields. There is a very concrete algebraic sense in which they are the same. Okay, so we'll see that. Anyway, when we get there, we will get there. But I just wanted to tell you this of the offset is that, like the way I'm going to try and structure is that I will try to somehow do maybe one or two algorithms at the end of every lecture. I mean, for the next maybe 4 or 5 lectures, where up until then we will learn maybe 1 or 2 tools, and then we will apply the tool for that algorithm. So slowly over the next few lectures, we will have enough tools to complete this entire module. Okay, so yeah, so just bear with things if suddenly it just feels like I'm just giving you properties which don't immediately seem applicable. Will soon end up getting used. So yeah, so the main task for this part of part B in some sense is going to be, I give you a polynomial over some field. At the moment, it's not clear what the field is, but let's keep it open for now. Okay, the coefficients are coming from some field. I want to compute its factorization into prime factors, and I want to do this efficiently. Okay, now, even though it seems like there's not much that I'm saying here, it seems like there is a lot of things that I need to clarify. The first thing seems to be like, what do you mean by prime factors? What does prime mean here? That's one thing that I need to clarify. And secondly, when I say compute its factorization, there seems to be some inherent assumption that these factorizations are unique, in the sense that I have a particular answer in mind and I want you to get that answer. Okay. And secondly, finally, when we're talking about efficiently, there's a question of, okay, what's our input size? And what sort of running times are we interested in? Okay, so these are some things that we need to clarify right at the outset. Okay, so let's first clarify what this notion of prime means. And traditionally, this prime is instead, the word that is used is irreducible. Okay, so what do I mean by that? So a polynomial is irreducible. Basically, your typical notion of what a prime number is. Okay, it's something that can't be decomposed into non-trivial factors. Okay, so formally speaking, you will say that a polynomial is irreducible over a field f, to mean that whenever I write f as g times h, where both g and h are elements, that whatever elements in this polynomial thing, basically such a factorization must be trivial in the sense that one of g or h must actually be a constant. It must be a scalar. There is no way to write down two polynomials of non-trivial degree whose coefficients all come from a field f, such that you can write f as a product of those two polynomials. Okay, that's what irreducible means. I do want to stress a few things, which is that it's important that we talk about irreducibility over a field f, because there may be polynomials that's irreducible over one field, but not over another. So a canonical example for this is the polynomial x squared plus 1. Over the reals, there is no way to write this as a product of two linear polynomials. But if your field was instead the complex numbers, then you know you can write this as x plus I into x minus I. So it's important to pay attention to what this field is. In the definition, this field plays a role in the sense that g and h both have coefficients that come from f. That's important. Okay, and I'm going to just, rather than prove these things, proving this is sort of like a digression and stuff like that. So I'll just tell you that the set of this polynomial ring, that is a ring made of whose coefficients come from some field, forms what is called a unique factorization domain. In the sense that, every polynomial can be uniquely written as a product of irreducible factors. Okay, one needs to be careful in the sense that, g times h and h times g, in my opinion, are the same factorization, and g times h and alpha g and 1 by alpha h are the same thing. So up to these silly ways of coming up with different factorizations, they are unique. So I'm not going to really qualify what unique means. You know what it means. Okay, so it so turns out that this notion of compute its factorization is a legitimate question when you're dealing with like coefficients coming from a field. Okay, so this is just to sort of, if you have some experience with ring theory or field theory, this will be there in almost any standard textbook in algebra. But I don't want to get into this because I don't think it's particularly useful for the sort of things that we are doing. And this is one of the things I think, it's very believable that this ought to be true. So I'm just going to leave it at that. And I'll add one more thing, which is a useful fact, which is that whenever you have a ring R that's a UFD, for example, such a ring could be Fx. Okay, then turns out if you add one more variable to the ring, it continues to stay a UFD. So the reason this is going to be important is because now I can say, oh, I can actually talk about unique factorization of multivariate polynomials, not necessarily univariate, because it's like I'm continuously using this fact again and again and again to add one variable at a time.
I have a question. So
yeah.
Is there some like non-pathological example of a ring which is not a UFD?
So I'm trying to, I think if I remember correctly, if you think of a ring where you add maybe square root of -5 to it or something, or one of these weird things, these are called these ring of Gaussian integers. So
just 5 here, or if you just consider z root 3 also, then you will get a if you just look, the example.
So actually, so this one, so look at the element 6. So 6 can be written as 2 times 3, but it stupidly can also be written as 1 plus root -5 into 1 minus root -5. And you can actually verify that 2 is a prime 3. 2 is irreducible, 3 is irreducible, this is irreducible, this is irreducible. So these are these weird examples where like there are factorizations, but there is no uniqueness. Okay, it's just, I mean, these are like pathological examples. We won't deal with it, which is why I'm sort of not spending too much time on this. But yeah, I mean, it's good to have these sort of markers on the road to say where we shouldn't stray. Okay, so yeah, so this is all like, I mean, at this point, this is just to tell you that when we are talking about compute its factorization, this is a legitimate question because there is, in some sense, there is a well-defined answer, and it's that answer that we are trying to compute. Okay, and something that will just end up getting used almost everywhere, okay, is this thing called the degree mantra. Okay, it's like it's one of these statements. It's like the pigeonhole principle or something. It's a completely trivial statement to make, but it's remarkable how many cool things you can prove with something as basic as this. Okay, it just says the following: a non-zero univariate polynomial whose degree is at most d can have at most d roots. Okay, and here is a one-line, I mean, proof of this. So basically, suppose if f of a is equal to 0, so this implies that x minus a divides f. I mean, this is, I mean, I'm hoping that every implication that I write is just relative, it's obvious to you. Okay, x minus a divides f. And this implies that if you think of h, which is equal to f divided by x minus a, has degree reduced by 1, and you just induct. So basically, what have you done? Any root for this guy, you removed one root and then you reduce the degree, and you will keep on doing this. The moment this thing becomes a constant, obviously you can't have any more roots. So that will tell you that you could not have started off with something where the number of roots was more than the degree. Okay, so yeah, there are possibly other ways of doing it. I mean, like this, in my opinion, is like the cleanest way of thinking about it. Okay, good. Okay, so I'm going to start off with some basic algorithms because I don't just want to bombard you with facts and properties about rings, etc. So I'll start off with an algorithm which hopefully you have seen in other contexts, you know, especially about computing GCDs of integers and so on. Okay, and we're going to do the same thing about computing GCDs over where we're dealing with polynomials instead of integers. Okay, so we just want to know among the factors of f and g, what is the greatest common divisor? Okay, and here when I mean greatest in terms of degree. So we're basically asking what is the largest degree polynomial that happens to divide both f and g. Okay, and I'm just going to write down the algorithm because I think you have seen this. I mean, like you must have seen this in, I don't know, MFCS or maybe in your undergrad or whatever. Okay, it's this completely simple algorithm which is just based on this observation that the GCD of f and g equals the GCD of g and f mod g. So you just keep repeatedly applying this again and again until the GCD is evident. Like when will the GCD be evident? Well, if g happens to be 0, then, well, f itself divides 0. I mean, anything divides 0. So f is the largest you can hope for. So in that case, you can just return f. And you just keep applying this again and again and again okay, so this is just meaning return GCD of, okay, this was probably a bad, this thing I should have probably written return GCD of these two things. Okay, it's an absolutely simple algorithm. You're just continuously, replacing the larger degree polynomial by the remainder with respect to the smaller degree polynomial, and you just keep doing this until one of the polynomials becomes 0. Okay, so why is this a polynomial time algorithm? So how many times would we have to do this process, like replacing it with a remainder?
At most the degree of the polynomial.
Degree of f and g. So therefore, this, whatever the number of recursive calls or this, whatever the stack size or whatever, is going to be bounded by whatever was the largest degree. I mean, it's maybe we can come up with a better bound, but nevertheless, this is certainly no more than that. And each of these steps is like something we can do in polynomial time. In fact, this is something we know we can do in linear time. Okay, so therefore, this is the GCD algorithm.
I have a small doubt.
Yeah.
So for us, primes and irreducibles are same or different?
I mean, I'm defining only irreducible polynomials. I'm not talking about what a prime polynomial is. But I was hoping to somehow sneak this into the problem set or something. We'll see. Okay, I mean, there may be a different notion of what a prime polynomial is, but yeah, I'll leave it at that. So right now we are talking about polynomials which can't be factorized more. That's what we are dealing with. So I know I'm sort of purposefully not answering Saurav's question because I'm hoping to add some version of this in the problem set. Yeah. Okay. So normally, I mean, like just like the GCD algorithm, there is something you can get more out of this, which is called the extended Euclid's algorithm. Okay. So this extended Euclid's algorithm, I mean, I don't know if again this is something that you have encountered in your MFCS course or something. So so basically, it's an algorithm that actually effectively shows that there always exist polynomials u and v such that u times f plus v times g is equal to the GCD of f and g. I mean, this is just basically doing some bookkeeping in addition to whatever this GCD computation was. Okay, and this is often written as the extended Euclid's algorithm. In my opinion, I mean, like the way I think of the extended Euclid's algorithm is like you maintain the following invariant, which is uf plus vg is equal to d. And you somehow force this particular invariant to always be maintained in your thing. So I currently have two copies. Okay, which I'm thinking of u prime, v prime, d prime. That's like the current version of u, v, and d. And this is like the one other version of u, v, and d. And we're going to successively keep doing things. I mean, we're going to keep improving this particular thing. And we have set it up such that whatever u prime f plus v prime g is equal to d prime. And uf plus vg is equal to d. So that's the base case in some sense. And if you forget about what happens to u and v, okay, if you just ignore these lines and just look at this algorithm, it's exactly the previous GCD algorithm. Like what is happening is like you start off with d prime and d is going to become d and the whatever, the mod business. So you're basically doing the GCD computation, except you're also updating u and v appropriately. So that's all that this particular thing is doing. And at the end, I was supposed to output d prime, but now along with d prime, I will output u prime and d prime, so that I am guaranteed that this d prime is equal to the GCD of f and g. And just the invariant says that u prime f plus v prime g is equal to d. So that's what the extended Euclid algorithm does. It does a bit more than just telling you what the GCD is. It tells you how you can get the GCD as a small combination of f and g. Okay, I'm just curious. So are there people who had not seen the extended Euclid algorithm before? Okay. Okay. So then I'm just going to just show why the invariant holds. So initially, I know the invariant was holding for these two pairs, but now those two pairs have been changed to this, and you somehow need to claim that the invariant continues to hold. This one is, I mean, there's nothing to prove there because this is basically the same that we have. So I need to show that after this modification, the invariant continues to hold. But that's sort of absolutely clear, which is what are we basically saying? We are saying look at u prime minus qu times f plus v prime minus qv times g. What is this equal to? This is like u prime f plus v prime g plus, or no, minus q into uf plus vg. This by whatever the previous invariant, I know this was equal to d prime. and I know that this was equal to D. So I get D prime minus QD, which is what we set this to. So the invariant is just maintained at every step. And the fact that you believe the GCD algorithm should mean that this also gives the right. Okay. So the main takeaway from this is this particular lemma. I guess it's called the extended Euclid postulate or whatever. I don't know. I mean, so basically, such an equation is also called a Bezout equation in some places. But basically, it says the following: I give you two polynomials f and g whose coefficients come from some field. Then turns out there are always polynomials u and v, such that if you look at uf plus vg, that turns out to be equal to the GCD. Like you can always find polynomials u and v such that you get the GCD exactly on the right hand side.
Same as we did in number theory, right? If GCD of two numbers is 1.
Yeah. So basically, you probably had seen the extended Euclid's algorithm for numbers. Okay, and we are just doing the same thing for polynomials. In some sense, nothing really changes. It's just that the notion of one number was smaller than some other number that is being replaced by the degree being smaller and stuff, etc., etc. So it's more or less the same thing. And what the algorithm above says that you can actually compute u, v, and the GCD efficiently. You can do this in polynomial time. Okay, so far so good.
I maybe slightly digression, but when the GCD is 1, so it's like if the question is if the problem is to decide if given two polynomials have GCD 1, then this is like once you have these ux and vx, if the answer is yes, then you can immediately check that it's yes. Like you just check that
if the answer to what is yes,
if the input polynomials have GCD 1. And if someone says, oh yes, they have GCD 1, here are the certificates ux and vx, then we can do this and we'll get 1. That immediately tells us yes.
Yeah, because so the point is, if f and g had a non-trivial factor, that will continue to be a factor of whatever you create here.
Right.
So therefore, if someone shows you how to get 1 out of this, you are forced to admit that f and g can't have any factor, because whatever factor that was supposed to divide 1, but nothing divides 1.
Yeah. But this is not true. Like if you want, like when the GCD is 1, these u and v give you a certificate that yes, it is 1. But if the GCD is like some other polynomial, then u and v do not act as certificate, because it's possible that something that divides GCD could be what the actual.
So in the sense that I find it a little weird to answer this question, because I can just ignore what certificate you are giving me and then compute it myself. Okay. Sorry, just 1 second. I don't know why I'm getting a call.
Can you repeat the question? I didn't get it.
So what I was saying is, if the question is like you want,
I missed it. I was sorry. What were you saying?
So Saurabh wanted me to just clarify what the question was again. So I was just saying that f and g are input polynomials, and you are like not only do you want to say okay, what's their GCD, but it's like, so this ux and vx that we get from this extended algorithm, if the GCD was 1, then they are in fact like proof that your GCD is 1, because you can just do ux into fx plus vx into gx from whatever you get as proof. I mean, you need not have calculated these by an algorithm or something. Let's say some person just told you, hey, I'm claiming that f and g have GCD 1, and here are the u and v that act as proof. Then you can like take this sum and you'll get 1, and that is it's easy to see that this is enough. And I was thinking, okay, that's not true if the GCD is not 1, because maybe what they have given you is something like when you take this sum of these products, then you could end up getting something which is which they say, oh, this is the GCD, but maybe the actual GCD is divides this thing. But then Ramprasad was saying, I mean, anyway, we care only about efficiently checking stuff. So that we can anyway do this in polynomial type.
Whatever you will get in the GCD of FG in that side, given the certificates even V, you have to show that if you divide by that factor, then always that will be lies in the ZFX. Then it will.
I mean, I guess Varun's point is that suppose let's say the GCD was x plus 1. That was the correct GCD.
Yes.
But someone gave you U and V such that it was x plus 1 the whole square. Now you additionally need to tell yourself that, actually I can't make the degree smaller or something. So it's currently at the moment, it's not a certificate to convince somebody that the GCD is x plus 1 the whole square. So, but I had a stupid solution to that to basically say, just ignore whatever certificate that the person gave you and just compute it on your own. And you'll know whether it's x plus 1 or x plus 1 the whole square. Yeah. I mean, it's not helpful, but hopefully, yeah.
I don't think my question was helpful to the class context either.
No, I mean, yeah, that I'm not sure of. I mean, okay, anyway, let's take this offline. Okay, so I'm doing the extended Euclid algorithm for a specific reason, because I want to now talk about finite fields in general. Okay, so I mean, we have seen certain examples of finite fields. By the way, just to recall to people what fields are. A field is something in which you can add, subtract, multiply, and divide anything that is non-zero. Okay, so it's a ring where you have this additional property that all non-zero elements actually have a multiplicative inverse. Okay, and everything is commutative. Okay, so things like the rational numbers, the real numbers, the complex numbers, etc. These were all fields. But we also saw that the set of all, for every prime p, you can just take your set to be 0, 1, 2, all the way till p minus 1, and just add and multiply, but do things mod p. And again, this is something that I presume you have seen in other places, that this actually forms a field. So the only tricky part is to show that inverses exist, but inverses do exist. It's relatively easy to see that. And fortunately, you have seen enough of ring theory, etc., to sort of say that if someone says this is basically Z mod PZ, you now know why this is the case. Okay, because this is just a representative for the residue classes when you go modulo this idea. So you end up getting P cosets. For each coset, you just pulled out one representative, which was 0 to P minus 1. Okay. And the question that one might want to know is, are there other finite fields? I mean, our finite fields basically things of the form you go mod P, where P is a prime, or can you come up with other examples of finite fields? And turns out the answer is yes. Again, this is also going to do with, you have to go mod P, where P is a prime, except that this prime is not a number anymore, but it's actually a polynomial. Okay, it's just that you need to expand your notion of what prime is. That's it. Okay, so I'm going to tell you an example of what a specific example of a finite field. Okay, so let's say the field you have constructed right now is F, and think of F as FP. Okay. And now you pick your favorite polynomial mu of t, which happens to be irreducible. It doesn't break up into smaller factors at all. And let's say that the degree of the polynomial was some r or something. Okay. And now what we are going to do is I'm going to look at the following object, which is look at all polynomials whose coefficients. I mean, I'm thinking of the variable as this parameter t or whatever. And the coefficients are coming from the base field that you have. But I go modulo mu of x. Again, this is something that you're familiar with. What are elements here? These are going to be a0 plus a1t plus blah, 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 plus ar minus 1 t power r minus 1, where all of these ai's come from your base field. Okay, this is because basically saying that mu of x is equal to 0 in some way, think of mu as a relation or something like that. It's like saying whenever you see t power r, replace it with whatever was the remaining part of mu of x. Because this is something that you have done when we adjoined roots to things and so on. Okay, it's exactly the same thing. And the claim is that this is a field. Okay, so we'll see a short proof of that. But let's get a sense of how many elements are there in this field.
P to the R.
So there are P to the R elements. I mean, if F is a field of size P, I mean, then basically there are P options for this, P options for this, and P options for this. So therefore, there are overall P to the R possible options that you have. Okay, so, okay, great. So therefore, you've just now constructed some set of P bar R elements. And this claim is saying that this set of P bar R elements is actually a field. Okay, and I think let's just take an example. So one example, for instance, is let's work over the field being F2. That's the base field, just so that because things are easy to deal with, which is just made up of elements 0 and 1. Okay, and let's take mu of t to be the polynomial t squared plus t plus 1. It turns out it is irreducible. Okay, so let's write down the multiplication table for this. Okay, and just to, I mean, like it's not a proof, but at least to convince ourselves that this is indeed a field. Okay, so 0 times, so what are the 4 elements? These are all linear polynomials in T, okay, whose coefficients come from F2. And there are only 4 such polynomials. There's a 0 polynomial, 1 polynomial, T, and 1 plus T. So those are the 4 points that you have. So let's look at the multiplication table. 0 is, I mean, like we know exactly what happens when we multiply by 0. Okay, and 1 also we know what happens when we multiply by 1 because it's the multiplicative identity. Okay, so what happens when I multiply t and t in this thing? So I get t squared, but I know t squared I'm supposed to replace it with minus t minus 1. But in F2 there is no difference between plus 1 and minus 1. They're both the same thing. So what you end up getting here is t plus 1. Okay, and if you look at t into 1 plus t, you get t squared plus t, which I know has to be equal to 1. Okay, the same thing, 1 plus t into 1 plus t is going to be t squared plus 2t plus 1. But I know 2t is 0 because 2 is 0 here. So I get t squared plus 1. So I end up getting t here. And then, oh, sorry. So this is 1 plus t into t. So that should have been a 1. And I get a t here. I mean, 1 plus t into 1 plus t, I get.
In multiplicative table, you don't consider 0, right?
Yeah, I mean, I just wrote down, I mean, for all the 4 field elements, when you multiply them, what do you get? I mean, you normally don't put 0 because that table is like a dirt table. I mean, so which is why you don't normally add this. But I'm just telling you what happens when you multiply every field element. By every element in this, I mean, at the moment, we will just say, I know it's a ring. I have no idea if it's a field. But once we write this down, it seems to be a field. Okay, so let's try to prove this in general. Okay, let's try to prove the above claim. That is, whenever mu is an irreducible polynomial, I want to claim that this is a field. Okay, so the only thing that you really need to show is this multiplicative inverse property to show that any, so whenever you pick up a polynomial f of t in whatever, over this thing with, I mean, any non-zero polynomial f of t with a degree of f, let's say strictly smaller than r. I used r, right, for the degree of mu. Yeah, the degree of mu is equal to r. So suppose you pick up any polynomial of degree smaller than r, I want to claim there is an inverse. There is an inverse u of t. I mean, what does this mean? It means that when you look at f of t times u of t, I want this to be equal to 1 mod mu of t. Because that's what products we were doing. We just take two polynomials, multiply it, go modulo mu of t. And I want to find a u of t such that this particular product becomes equal to 1. Okay. Now, the fact that I wrote it as u of t should hopefully be indicative of something.
Use this GCD algorithm.
Okay. So basically, it seems like this u of t must be one of this extended Euclid stuff. Because I know that uf plus vg is equal to the GCD. We need to now figure out what is this g that we are supposed to use. Okay. So let's just write this down. Okay. What does something being 1 mod u of t mean? Okay. So it means that f of t u of t equals 1 plus some nonsense v of t times mu of t. Because going mod, I mean, like the mod mu of t just means that I'm ignoring any multiple of mu of t. Okay. Now this is already starting to look like one of those extended Euclid sums. Okay. So, I mean, so now the point is, let's ask ourselves, what is the GCD of f of t and u of t? Sorry, not u of t, mu of t. Well, I know for a fact mu is an irreducible polynomial, which basically means, so firstly, if whatever is this GCD, its degree must be smaller than or equal to whatever the degree of f was. So the GCD has to have degree strictly smaller than r. What are possible factors of mu of t that have degree smaller than r? Well, there are none besides the stupid 1 thing. Right? So therefore, this GCD is just 1. So what's happening is that because this GCD was 1, okay, all of this was like this is like thought process. Like this wasn't the proof of it. This is what we are trying to get to. So the formal proof is the following. We know for a fact that the GCD of f and mu is equal to 1. So the extended Euclid algorithm tells you that there are some u and v such that u of t f of t plus v of t mu of t is equal to 1, which basically implies that u of t f of t is equal to 1 mod mu of t. And that's a proof of the fact that you take any non-zero polynomial that you want. The fact that it has smaller degree and it is non-zero means that the GCD is 1. So you will find something, some u such that u times f is equal to 1. So again, the extended Euclid algorithm not only says that this is a field, it actually gives you an algorithm to invert one of these elements. Like somebody now gives you an element in this thing and says, can you tell me what the inverse of this is? I mean, you basically only need to run the extended Euclid algorithm of whatever that element was with mu of x. So then you compute the inverse. Okay, I hope this was clear. How you construct fields. So this basically says that there are fields of the form fp, which are one of your standard finite fields, which is just, you look at the residue classes modulo p, where p is a prime integer. Or you can construct fields of the form fp power r, which is you start with a field fp, and then you go modulo one of the irreducible polynomials. Then you get a field of prime p power r. Okay. And these sort of fields are called characteristic p fields. Okay, there's a notion of called characteristic, which is like how many times do you need to keep adding 1 so that it becomes 0. Turns out both of these fields, if you just keep adding 1 to itself p times, it becomes 0. And just to confuse things like rationals, complex numbers are called characteristic 0 fields and not characteristic infinity fields. But whatever. So Yeah, so there's notion of what characteristic is. I don't think it will matter much enough.
Hey,
So
also,
yeah,
for over any field, like for any R, like is it easy to get irreducible polynomials?
so it turns out that irreducible polynomials are in plenty. Okay, there are like plenty of irreducible polynomials. There's actually a nice short proof of this. In fact, it sort of it again follows the typical thing of the prime numbers. You know? So, for example, if you look at if you want to know how many prime numbers are there between 1 and n, okay, the prime number theorem, I mean, if you have seen this in other contexts, will tell you that there are about n by log n prime numbers. Now, if you again ask the following question, how many irreducible polynomials are there of degree n? Well, the total number of polynomials is like p power n. Okay, turns out roughly 1 over log of that are irreducible polynomials. So in some sense, the density of irreducible polynomials is very similar. So it turns out that, I mean, many times what happens is you just pick a polynomial at random. And if you can figure out how to test whether something is irreducible, I mean, you have an irreducible polynomial. So that's usually how it works. It turns out there are actually algorithms to pick an irreducible polynomial directly. But we won't be doing that in the course. But yeah, it just turns out that for every degree R, there are plenty of irreducible polynomials. Okay, so turns out that basically these are the only finite fields. Okay, and again, I'm just asking you to take this for granted. I'm not proving it, but I'm just telling you that turns out this is what it is. And in fact, there is something a lot more that is known. Now, I gave you one particular construction of a finite field of size p power r, which is I said, take an irreducible polynomial, you get a finite field out of it. Now, I could have picked up one particular polynomial, constructed one field. Now, maybe you picked up a different irreducible polynomial and constructed a different field of size p power r. Now, turns out we are both constructing the same field, we are just naming things differently. So that's actually a pretty powerful result that basically says that even though it seems like I'm telling you how to construct a finite field of size p power r, turns out there is just one. And we might just be calling things differently. They are all isomorphic to each other. Okay. Again, these are all facts that that it's good to know, but you wouldn't have to prove it, or the proofs are not necessary for what we will be doing in this course, which is why I am not doing this. I mean, yeah, but there are plenty of cool, fun things to know about finite fields. Okay, so are there any questions up until now? It's at least the construction of finite fields clear.
And that thing that you mentioned about it being like, so this is the case. It's not just that you take any other irreducible polynomial and you get like you stay isomorphic to what you have.
No, you do. So the sense that
I mean it is. I'm saying much more than that. Even if you are doing something crazy that doesn't even involve like no matter exactly how you create FPR,
no matter how you create a field of size fp power r, it is isomorphic to, maybe I have my favorite degree r irreducible polynomial. So in my opinion, I have a field of size p power r, which I constructed via ft quotiented by mu of t. No matter what other person comes up with a field of size p power r, these two things are isomorphic. We are just calling elements maybe by different names, but once we relabel them, multiplication, addition, we are doing the same. So it's a pretty strong result in the sense that here are the finite fields and these are precisely what the fields are. I'm not just telling you there are fields of size p and size p power r. I'm telling you exactly what the fields are. Okay.
And if you're not a prime power, you can't create it.
You can't have fields. If p is not a prime, and I mean if you can't have a field whose size has two different prime factors.
Is that easier to prove than showing this isomorph?
Actually, that is easier to see. I'll maybe let you think about it more. Yeah. Okay. Okay, great. So this, at least now what we have done is we'll be dealing with polynomials coming from finite fields, and we at least now know what those finite fields are. Okay, these finite fields will most often be something of the form fp, but sometimes it might be something like of the form fp power. Okay, so I hope so far things are clear. So next I want to tell you about this cool fact, okay, which is it's incredibly useful, this particular thing, which is, so here is the question, which is, let's fix any finite field of your choice. Maybe there's a field of size p power r. Okay, let's fix fp power r. And let's consider the following polynomial. So what I'm doing is I'm taking every element in my field and just looking at x minus alpha. Okay, and I want to know what is this polynomial. If I multiply everything together, what do I end up getting? Okay, let's try out a few examples. Okay, I am not doing it for p power r here. I'm doing a cop out and choosing just fp. But I'm hoping that that will give us some idea of what this polynomial should be. So if I take x into x minus 1, I end up with x squared minus x. If I take x into x minus 1 into x minus 2, this is what? X into x squared minus 3x plus 2. But mod 3, this doesn't make sense. I mean, like the 3 is equal to 0. So in fact, you will get x squared minus x. Sorry, x cubed minus x. And if you do it for mod 5, I mean, trust me, and you will end up getting x power 5 minus x. Okay, so it sort of, I mean, something is going on here. I mean, it seems to suggest that, in fact, this should just be x power p power r minus x.
This looks very, this basically looks like Fermat's little theorem.
Yeah, and in fact it is. I mean, we'll see that, you know, it's basically Fermat's little theorem, except you're doing it over general finite fields and not just this thing. So let's see a short proof of why this is the case. Okay, so firstly, one thing to keep in, I mean, these sort of sanity checks is always useful. The left-hand side is a polynomial of degree p power r, because there are p power r terms. And the right-hand side is also a polynomial of degree p power r. Okay, so it makes sense. And maybe one thing to figure out is, what is the constant term of the left-hand side? Well, it's actually 0, because one of those terms, one of the elements in the field is actually 0. So one of these factors is actually x minus 0. So it's x. So the constant term being 0 also makes sense. The coefficient of the leading term is equal to 1, because all of them have 1 in its leading term. So these sort of basic sanity checks seem to work, but why the hell is this equal to? Is this the same? Okay, and the way we are going to do it is using the degree mantra. Okay, I'm just going to show that this particular polynomial has p power r roots, which are basically all the different elements in this field. And like we said, that, you know, degree, I mean, like if this answer and this answer were different, then somehow their difference seem to have the same set of roots, and that's not possible. Okay, so that's what we're going to do. We're just going to show that this is divisible by x minus a for every, or x minus alpha for every alpha in the field. Okay, so I'll basically say, okay, so now fix any alpha in fp power r. Okay, so the claim claim that x minus alpha divides the right hand side. I mean, if you can prove this, we are done, because that will basically say that whatever this thing is, it better be some constant times the product of x minus alphas. And we know that constant has to be 1 because the leading term is 1. Okay, so this is, okay. So now I just need to do some stupid case analysis. So suppose alpha was equal to 0. Okay, then clearly x divides the right hand side. Then clearly x divides RHS. So this part is done. So suppose alpha was not equal to 0. Okay, then want to say that x minus alpha divides x power p power r minus 1 minus 1. That is, I know the right hand side, this is equal to x into x power p power r minus 1 minus 1. Okay, and I want to say, okay, the 0 thing divides this guy, every other thing divides this guy. That's what I'm trying to say. Now, why is this true? Okay, so here is the trick. So you basically look at the following set, which is 1 alpha, alpha squared, alpha cube, etc., until I get to some alpha per k minus 1, and maybe alpha per k is equal to 1 again. Okay, basically I'm just saying, look at all the things you can generate using just alpha, multiply it. Okay, I mean, I'll let you, or in other words, let me put it this way. Okay, let k be equal to the smallest integer such that alpha per k, this is equal to 1. I mean, smallest non-zero. Okay, this is also called the order of alpha. Okay, so what does this mean? This means that if I look at 1 alpha, alpha squared, etc., alpha to the k minus 1, okay, this is a subset of f p power r minus the 0 thing. If I remove, I mean, I'm right, this is such a stupid statement to make, because if alpha is non-zero, obviously a power of alpha cannot suddenly become 0. Then I can't invert things.
So it's a multiplicative group if you just look at it.
The fact that it is a field means that this is a group. And it's not just a subset, this is actually a subgroup. That's a group. Okay, and this tells us, Lagrange's theorem tells us that the size of this group must divide this thing, the size of the right hand side. So this implies that k must divide p power r minus 1. Okay, which means if I look at alpha power p power r minus 1, this is equal to alpha power k times something. I don't know what that is. Okay, which I know is equal to 1, because alpha per k is equal to 1. So that tells me that alpha satisfies x power p power r minus x, or x power p power r minus 1 minus 1. Okay, and that basically tells us that you can choose your favorite, or any alpha that you want from this field. Turns out the polynomial x minus alpha divides the right hand side. And you've just found p power r factors for a polynomial of degree p power r, which basically means these are all the factors. I mean, you can't have anything else. Okay. Okay, great. So this is I mean, it turns out to be an extremely powerful observation to have. And I mean, this is going to help us a lot in designing these factorization algorithms. So let's take a few examples of, so let's work over F2 or something. And if you just try to factorize all of these things, I mean, x power p power r minus x's, the way I have written above, okay, you get terms of, so for example, x squared minus x becomes x into x minus 1. I mean, this is a trivial factorization. X power 4 minus x becomes x into x minus 1 into whatever this thing is. So this is like an irreducible polynomial of degree 2. So when you are adding this, I mean, if you're adding a root of this polynomial, you're adding in something that was outside of F2, which is why you end up with a slightly larger field in some sense. Okay, if you look at x power 8 minus x, then you have a bunch of things. And if you look at x power 16 minus x, why I have this equality here. Okay, x power 16 minus x, you again have a bunch of things. But it looks like this guy is a factor of this guy. Okay, so there's something unusual happening here, which I'm going to try and demystify at this point. Okay, so it's just that if you factorize these x power 8 minus x and x power 16 minus x, etc., it splits into irreducible factors over the base field. Like had I factorized this over the field F4, it will actually split into 4 linear factors. I mean, because that's what this thing is. But if you're factorizing over F2, maybe some of those factors, I mean, like, you can't write them over F2, which is why you have one. Okay, now let's ask ourselves mentally. Suppose you wanted to add an element of, add a root of the polynomial x squared plus x plus 1 to your field. Like we added one of those principal roots of unities and so on. What would you do? Okay, so I'm just saying that if you, how do we add a root of x squared plus x plus 1 to F2? What we would have done is basically say, let's look at this particular object, which is x squared plus x plus 1. Okay, and turns out this was this field F4 that we just constructed. Okay, so it's this weird thing where you added a root of one polynomial and you got some ring, and that ring turned out to be a field. Okay, now let's imagine adding the root of this polynomial, x cubed plus x plus 1. Okay, so that will amount to doing x cubed plus x plus 1 here, which was the field F8 that we constructed. So what did we really do? We basically said, the picture was something like this. The way F8 was constructed was that I had this point 0 and 1. Okay, this is my field F2. This is the base field that I started off with. Okay, and I basically said, I want to somehow artificially add one of the roots of x cubed plus x plus 1. Okay, so I ended up adding one of those roots. This was what the polynomial x refers to in this thing. Okay, but as you can imagine, once you add one thing, you need to add a whole bunch of other stuff. Like for complex numbers, you added I, and now you were forced to add a plus ib for a whole bunch of things. And what ended up happening is that you ended up adding a few more elements. And you ended up with totally 8 elements in this thing that you are studying. Okay, so the funny thing that happens is that these 3 points turns out to be roots of the polynomial x cubed plus x plus 1. And the other 3 points turn out to be roots of x cubed plus x squared plus 1. Okay, so this is bizarre thing where you actually only intended to add a root of this irreducible polynomial. Okay, but someone else who wanted to add a root of this irreducible polynomial might have added one of these points. It just magically happens that once you add a root of one irreducible polynomial of degree r, you somehow end up adding the roots of all irreducible polynomials of degree r, which is something bizarre that happens over finite fields. With this thing. Okay, and I let you stare at this picture more, and you can actually convince yourself that something far stronger happens, which is that it is not the case. It's very easy to somehow have a knee-jerk reaction to sort of say that I know F2 is a subset of F4, because inside any F4 there is one copy of F2 sitting inside, and you might think that this is a subfield of F8, but this is not true. Okay, so it turns out that Fp power r is a subfield of Fp power s, if and only if r divides s. Just notice that what would the picture be when you wanted to add F4? So there is 0, there is 1, and then you ended up adding a root of the polynomial x squared plus x plus 1. So that will be 2 other points. Okay, so these are whatever roots of x squared plus x plus 1. I mean, this picture is not present in this picture at all. Okay, so I mean, this is not a good proof of this, but I'm just trying to illustrate as to why just because one has 4 elements and the other has 8 elements does not mean these 4 elements are contained in those 8 elements. So there's something a little different that happens here, which is that f p power r is a subset, it's a subfield of f p power s if and only if r divides s. So for example, f4 will be a subfield of f16, but not of f8. Okay, these are some weird nuances that one needs to get comfortable. I mean, don't just assume that because they're all powers of 2, like one is contained in another is contained in another, etc. It's a slightly more nuanced picture in how these fields sort of interact with each other. But nevertheless, in fact, it turns out that this factorization reveals so much more information. Okay, it actually says, because this factorizes in this form, and you see 3 irreducible factors of degree 4, turns out these are all the irreducible factors of that degree. Okay, like, I mean, it just so happens that, so in fact, let me just write down the proposition. I mean, these are things I'm not going to prove, but we are just going to use it. Okay, so here is precisely the thing. Suppose you take this expression and factorize it over fp. That is, you're only looking at the factorization over fp. Then what are the factors that you end up getting? Turns out you will end up getting a factor which is every irreducible polynomial, which is monic, such that its degree divides this r. So which is why when you're looking at x bar, okay, let me write this as, this is x bar 2 squared minus x. So this is a product of all irreducible polynomials of degree 1 and 2. Okay, and if you look at x cube minus x, which is like x bar 2 cube minus x, this is going to be all irreducible polynomials of degree 1 and 3. Okay, and this is like x bar 2 bar 4 minus x, which is all irreducible polynomials of degree 1, 2, and 4. Okay, so it's a remarkable factorization. And in fact, going back to the question that Varun had asked, how do you prove that there are many irreducible polynomials of a certain degree? In fact, you use expressions of this sort to do this. I mean, overall, you need to add up to degree 16. So it better be the case that there are sufficiently many polynomials of degree 4 and degree 2, etc., so that they all add up to 16. And you can play around with those sums and show that there must actually be many, many of them. So that's usually how people prove that that is there. But okay, I completely understand that this is a lot to take in. But let me just pause and say that here is what I would like you to take away from it. The rest of it are details which I hope you can, whenever needed, you can explore more and learn more. But these are the 2 key points that I will ask you to take. Okay, which is that not all fields that are characteristic P fields are contained in one another. Don't make that assumption. It is not true. It happens only in this. It happens even only if the r, whatever, the 2 exponents divide each other. That's one thing. And this particular equation is super, super useful. So just tell yourself that whenever you're looking at x power p power r minus x, the factorization over fp is basically the product of all irreducible polynomials of the right degree. And the right degree just means the degree must divide r. Okay, so this is what I mean, these are the main properties I'm hoping that you can absorb in this particular lecture. And in the remaining about 10 minutes, we are going to use this property for one algorithm. Okay, and hopefully that will let this sink in a bit more. Okay, maybe let me just stop here and make sure if there are any questions, if there's something that is unclear, if you want me to go over something, etc. Okay, so okay, so again, let me just say that let's just keep this in mind. This is a very, very important fact to know. It's going to be very useful. Okay. So here is the first algorithm that I want, besides the GCD algorithm that I want to tell you, first non-trivial algorithm, which is irreducibility testing. Okay. This again goes back to our original question where we were basically saying, the task I'm hoping to compute eventually is given a polynomial, find its irreducible factorization. But somehow it feels like the basic thing that you need at this point is that suppose somebody gives you a factorization and says, hey, I have factored the polynomial into irreducible factors. Would you believe them or not? Like, how would you convince yourself that this is actually the factorization? One thing you can do is you can multiply the factorization and make sure that it still equals the polynomial you are computing. But what is unclear is, well, is the factorization made up of prime numbers or not? Or other irreducible polynomials or not? So you need some way of testing whether a polynomial is irreducible or not. Okay, so that's the algorithm we are going to see now. Okay, good. So before that, what is the input length? From this point, we're going to be dealing with all operations matter. When we are multiplying two numbers mod p, we are thinking of them as two integers being multiplied, etc. So if the degree of the polynomial, normally we will say that this has degree d. I'll use d for the degree. In that case, the input length is going to basically be equal to d log p bits. Is that okay so far? Because there are to be really precise, it's like d plus 1 log p. So there are d plus 1 coefficients in f, and each one is an element of fp. So therefore, it is specified using log p bits. Okay, and therefore, I want a running time which is supposed to be polynomial in log f and log p. This is the gold standard. This is the sort of running time I'm willing to tolerate. So I want it to be poly in d comma log p. Okay. So does someone have some thoughts on how we can go about irreducibility testing? Maybe let's start with the simpler thing, which is that I give you a degree 2 polynomial and I want to know if it is irreducible or not. Okay. So if it is not irreducible, it will split into two linear factors. Okay. A linear factor must be of the form x minus alpha, where alpha is in your field. Right. So one possibility that you could do is go over every element alpha in your field and see if it satisfies this quadratic polynomial or not. Right. So that is one possible way of testing. Does x minus alpha divide this polynomial? And I'll just run over every possible alpha and check if x minus alpha divides the polynomial or not. Why is this not an algorithm that one should be satisfied?
We want poly log p and degree.
That's right. Because currently this algorithm is taking p time and not log p time. Okay, so that is something that I'm not willing to tolerate. I want log. So that's, at least this is a baby step here. Okay, but okay. So here is what here is a hint that I'll give you. If f was not irreducible, okay, then f has some irreducible factor of degree. In fact, I can say of degree at most degree of f by 2. Because just take the, f splits into two factors. Just take the smaller of the two factors or something like that. So if f is not irreducible, there must be some irreducible factor of f whose degree is no more than d by 2. Okay, now is there a way of somehow pulling that out? Getting our hands on let's say I don't even want to know what this mu of x is. I just want to know, does such a mu of x exist or not? Okay, so I'll give you one more hint, which is that f is irreducible. I mean, so suppose f had such an irreducible this thing. I want to say then the GCD of f with something is non-trivial. Okay, what should this something be? I mean, can you come up with a polynomial that actually is, I mean, that has mu of x as one of its factors? Because then if I take its GCD, I will end up with, I don't know if I'm making sense here. Okay, so let's go back to those things. I mean, so these are the sort of polynomials that I know are there, I mean, present here. So this involves all irreducible polynomials of degree 1 and 2. This involves all irreducible polynomials of degree 1 and 3, etc., etc., etc. So if mu is a polynomial of degree d by 2, okay, and if I consider whatever x power p power d by 2 minus x, mu will show up on the right hand side. Right? I mean, all I'm saying is that then GCD of f with x power p power r minus x is not equal to 1 for r equal to degree of mu. Is this okay? I mean, because when we expand x power p power r minus x, what will we end up getting? This, the takeaway from this big bunch of stuff that we did earlier, says that x power p power r minus x is a product of all irreducible polynomials whose degree divides r. In particular, this mu of x that happens to divide f must show up on the right hand side. So whatever that mu of x was, that is something that divides this guy, and it also divides f. So in particular, it must be not equal to 1. So the algorithm is sort of is super simple. So it just say for a going from okay, we used r, so let me use r again, 1 all the way till d by 2. Okay, if GCD of f with x power p power r minus x, this is not equal to 1, return false. Okay, else return true. Okay, is the correctness clear? This is just using the fact that if mu had degree r, I know the GCD of this is at least mu of x. It may be more, but it's at least mu of x. Okay, but on the other hand, if f was irreducible by itself, then I mean, then it should not be divisible. I mean, there must be no common factor with x power p power r minus x, because this only involves irreducible polynomials of degree r or lower. Okay, so if f was irreducible, all of them will be equal to 1, so you will return true. And if f was not irreducible, the moment you hit that threshold of whatever the irreducible factor's degree, you will end up with a non-trivial GCD, and you know that the answer is 1. Okay, fairly simple algorithm, but don't buy this algorithm immediately, because what's the running time of this algorithm?
what was the running time of the GCD algorithm?
It was basically polynomial in the degrees involved.
So then this is
right now. This degree is massive. I mean, last time even p we couldn't tolerate. Now I'm saying that you work with p power d by 2 or whatever. So the degree is huge. But you can actually do something. So basically, we want to know, how do you compute this? So any thoughts?
Sorry, how do you come up with?
I mean, this is the GCD I want to compute. But I can't afford to write down the polynomial x power p power r minus x. So I need to do something clever. Okay, let's do one step of the GCD algorithm, which is, so we have GCD of f with x power p power r minus x. What would we do in the very next step? We'll basically say this is equal to GCD of x power p power r minus x mod f and f. Now what's the degree of this guy? It's at most d, where d was the degree of f. Okay, so if I can get here, then I can run the GCD algorithm that we had earlier. Okay, so what I want to do is I want to compute this guy. I mean, the problem completely boils down to, can I do one step of the GCD algorithm without doing the usual mod business? Can I somehow do something clever? Okay. So let me ask you, suppose I gave you a number which is 3 power 171435 mod 5. How would you compute this number mod 5? Or okay, mod 5 was maybe bad. Let's say mod 42, something. I'm hoping you have seen this in one of your MFCS course or algorithms course or something.
Yeah, so you can basically write this as some.
Okay, let me make life a little easier for you. Suppose this was 65536. I don't know if you recognize this number. Okay. Let me make it as 1024.
That's some powers of 2.
Right. So suppose you manage to compute what is 3 power 512 mod 42.
Then it's just square.
Okay. So this is going to be eventually, once I compute it, it's some number between 1 and 40. Sorry, 0 and 41. Okay. So I need to square that and figure this out. So this thing is called repeated squaring. I don't know if people have seen this before. I mean, so let me just, okay, so I'm just going to write down what you need to do. So this is basically, I'll write this as GCD of x power p power r mod f minus x comma f. Okay, and the way we will compute this is using repeated squaring. So what I will do is, like x power p power r, suppose it was, I don't know, x power 81 mod f. This I'm going to write it as x power 40 into x power 40 into x. So I will recursively compute x power 40 mod x, square that, and then multiply it with x, and then do mod again. By the way, have people not seen repeated squaring? Then I'll do this more explicitly.
And also, like, I mean, and here again, like, I think something that helps in doing these calculations quickly is like, okay, you can do this repeated squaring thing, but also if you are working in like this Fermat's written thing, you can use that, right? If you are,
no, x is a formal variable currently, so one needs to be a little careful. Okay, since I'm getting some blank this thing, I'm going to just try and do this explicitly. Okay, so let me just write down this thing. So here is the algorithm, okay, which is to compute x power k mod f. Okay, that's the task. I am given k and I'm given f. I want to compute x power k mod f in time poly in the degree of f and log k. That's the goal. Okay, so what do you do? So the point is, if k is equal to 2l, that is, it's an even number. Okay, so what I'm going to do is I'm say let g be equal to x power l mod f. This is a recursive computation. Okay, now you return g squared mod. Okay, that is if this happens. So else, okay, let's say k is equal to 2l plus 1. Okay, once again you compute g is equal to x power l mod f and return g squared into x mod f. Okay, is it okay so far? Like, okay, so what's the running time of this algorithm? So if t of k comma d is the time taken to compute this guy, this basically ends up requiring one call of this recursive algorithm. Whether you go into this branch or this branch, it's still one call of t of, it's like roughly k by 2 and then t. And which eventually you just get that this is going to be poly in log k comma t. Was this okay? I mean, like, I hope I'm not like just, I hope people are able to follow what's going on here. So this is in general called repeated squaring. That is that whenever you have x power something and you want to reduce modulo whatever, there's a way of doing it rather than just multiplying x with itself k times. You can do these sort of big jumps, which is where you square every time and then just handle this even and odd case appropriately. Okay, so basically what happened, what you need to do in the process is that computing this GCD of x power p power r mod f, this only takes time which is poly in the degree of f, which is d, and log of this guy, which is r log t. And r is never going to be more than d, so therefore this entire thing takes poly in d time, d comma log t time. Okay, so since we are running out of time, let me just summarize what we saw here. We saw how to construct finite fields, and I will sort of again insist that I mean there was some attempt to demystify what was happening here, but think of this as the main takeaways, which is that the polynomial x power p power r minus x splits in a very, very nice form, which is the product of all irreducible polynomials of suitable degrees. Okay, so that's how it ends up splitting. And we use that fact to basically do irreducibility testing. We said that if f was not an irreducible polynomial, it has some irreducible factor which was smaller, and that irreducible factor will show up in one of these products. So let's take a GCD with that product and see if the GCD is 1 or not 1. Okay, and that's what we did, except there was one slight nuance, which is that the polynomial you're taking GCD with, it's a massive degree polynomial. But you can use repeated squaring to actually do one step of the algorithm in a slightly clever fashion. so that you are now dealing with a GCD of 2 polynomials of degree at most b, and then you proceed from there in the standard form. Okay, so that's what. So that was the irreducibility testing algorithm. So at least now we know, given a purported factorization, we can at least check whether the factorization is correct or not. Okay. So in the next class, okay, we'll get time to do that. So what I plan to do in the next class is the following. We'll do this notion of what is called distinct degree factorization, which is I may not be able to factorize a polynomial completely, but I might be able to say, by the way, all linear factors are contained here, all quadratic factors are contained here, all cubic factors are contained here, etc., etc. You split them based on its degree. But then you will have this task of taking a polynomial, all of whose irreducible factors have the same degree, and somehow splitting them up. We need to figure out what to do. That's going to be the main part of this univariate factorization. And we'll also have to deal with these repeated factors. Sometimes you might have a polynomial where the same, it shows up as x plus 1 the whole squared or something. So we need to know how to deal with such repeated factors. And once we do that, we'll actually have an algorithm that factorizes all univariate polynomials over finite fields. So in the next class, hopefully we'll at least figure out how to factor univariate polynomials over finite fields. And then we'll build on top of that to go to bivariates, etc., etc. Okay, so that's all I wanted to do today. I will try to post a problem set either this weekend or early next week. So that you get a little more comfortable with fields and rings, etc., because they will end up being we'll deal with them in more more intensely over the next couple of lectures. Okay, are there any questions? Okay, if not, we will just meet on Tuesday next. Okay.